right there. So a body in translational equilibrium have no motion in the x or y or z direction. However, it's still free to rotate though, right? So it could be rotating, counterclockwise or clockwise. Now for rotation, we usually only care about the direction of counterclockwise or clockwise, because rotating, you can't really say you're rotating to the left or rotating to the right. That doesn't make any sense. So for an object, for example, let's say you have a can, like a can of like soft drink. I mean, we only talk about rotation in two different directions. Either you're rotating this way. So when you're turning this way, now if you ever forget like which way is clockwise, which way is counterclockwise, just look at the clock that we have in class. So clockwise is when you're turning in this direction, so clockwise, right? And counterclockwise, of course, obviously, is just the opposite direction, like right here. So counterclockwise. Now, I don't need you to spell out the word clockwise and counterclockwise. Just use the shorthand CW and CCW for the direction. So if you need to know which way the object is rotating, then you can either answer clockwise or counterclockwise. You can just use that distinction. Okay, so consider something like a theater, which you might have a chance to play in a playground when you're younger, right? So usually, or we call it a seesaw. So usually, in a game like this, now imagine what happened is, let's say I put one end, a children that is 100 kilogram. On the other hand, another children that is 50 kilogram, right? So 100 kilogram on one end and a 50 kilogram children on the other end. Now, if you draw the free body diagram on this system, you will notice that, okay, so I have FG1 and for the 100 kilogram student, and I have FG2 for the 200 kilogram, for the 50 kilogram student. Now, there is a point of support though in the middle. So that point of support is going to provide us with electron-electron repulsion, which is normal force. So that point of support is going to give us that normal force. Like right here, the normal force, right? So is the electron on the support repelling the electron on the piece of wood board that you're sitting on. Now, this makes perfect sense. And when you look at the system like this, let's look at all the forces in x and y direction. Now, forces in x direction isn't even there. So in the x direction, we have all the forces adding up to, well, 0. It makes sense because there isn't even a force in the x direction at all. Now, but what about in the y direction? What about the y direction? In the y direction, we do have forces. We have Fg1, Fg2, and normal force. But we know how normal force works. Normal force is always trying to just, balance things out, right? So we know that in the y direction, all the forces also are supposed to add to 0. This system will not go up or down. So what can that tell us about the normal force? Well, then that means the normal force must be at least, well, not at least, must be exactly Fg1 plus Fg2. Otherwise, this system will collapse. Now, so there is no net force in this system. This system will not go up or submerge underground or suddenly start flying. You know that this doesn't happen because you have been on one of these games in your past. You know that the whole platform doesn't just go up and down. But however, even though all the forces add to 0, can you be certain that this thing won't rotate though? Like when you look at this picture, does it look like it's going to rotate or not? Think about it. Does it look like it's going to rotate or not? Imagine you put your brother here and you put your younger sister over there. Will this system rotate? Will it? One side is heavier than the other side though. Think about it. So if you have a system, for example, where you put two equally mass objects on each side, then it should be stable, right? But if one side, for example, in this case, the left-hand side is heavier than the right-hand side, wouldn't the system go this way? That's like a logical thing to expect, and this will happen. I mean, that is exactly what will happen once you let go of the two kids. The 100 kilogram kid on the left-hand side is going to sink lower to the ground, and the 50 kilogram kids on the right-hand side is going to rise up. The system is going to rotate in counterclockwise direction, in this case, right? So that means even though this system is in translational equilibrium, that means all the forces balance out, the entire platform won't go up and down, but this system has a net torque on it. That means it has a force that will cause it to rotate. Torque. Okay, let torque on it. So it's not in perfect equilibrium yet. In order for an object to be absolutely in equilibrium, it has to both satisfy the translation equilibrium condition, which is having all the forces in x and y direction completely balance out. That's condition number 1. Condition number 2 is you also have to eliminate all the torque, and that is called rotational equilibrium. When you are trying to iron out or eliminate all the torque, okay, it's called rotational equilibrium. So in order for a system to be truly stable, no movement at all, which as an engineer is like the basic requirement that your boss is going to ask you to do. Make me a building, don't let it move, don't let it rotate, don't let it do like anything stupid that it's not supposed to be doing. Well, you have to balance two things. Balance all the forces, which is called translational equilibrium, and balance all the rotation so that your object doesn't just spin around on its own. Balancing all the rotation is an act of balancing all the torque in the system. Torque is a force that makes something move. Now, in physics, we would like to use, torque, right? T. So can we just use T as a symbol? Well, but unfortunately, T is already used for two other things. For example, time and temperature is already using T, right? In our alphabet, in the equation. So we can use T again for like the third time in something that are so related. So therefore, we are going to borrow T, the character, from, again, another language, from Greek. This is T. Okay, T, torque. So now this T, well, technically it's like this, right? Like this, like this. Okay, so this is torque in the equation. Okay, now this is actually the Greek character of T. Its name is tau. T-A-O, tau, 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 tau. Okay, so but we'll just say torque. So torque. So we will need to make sure that all the torque also balance out. So all the forces should balance out, and all the torque should also balance out. All right. So what is torque and how do you calculate it? And after, well, how do you balance it? Well, next step. Okay, so the second condition, which is called no rotation, there must be no net torque. No torque should be on it. Torque is defined as a force that causes the rotation. So torque has an equation that is very, very easy to use. The amount of torque trying to rotate the object is equal to the force multiplied by the distance that the force is applying on to the pivot. Now here, we have a new word. I mean, maybe not new. Maybe you already know what pivots are. Pivot is a point of the center of the rotation. Now, but you have to think about it like this though. Pivot is not always going to be the same point. For example, if you have a pencil, right? This is a pencil. Some people spin the pencil, right? It's a habit. Cool things to do. But if I ask you, what is the pivot point on a pencil? Well, it depends on how you're trying to spin it. Some people might spin the pencil from its end. So the pencil spin like this. Well, that's good. So that the end of the pencil is the pivot. But couldn't you also spin the pencil from the middle? You could. Then the object would go like this. It would just spin around the middle, right? So technically speaking, the pivot is any point that you want it to be, because you can spin an object along any point, right? There's no physical limitation on which point you have to spin the object from. Now, unless you're talking about like a tire, which does have an axle in the middle, so it's kind of like, oh yeah, the pivot is right in the middle because it's already set up for you. But if you're talking about, for example, like a board like this, like just this board right here, well, technically you can spin it from the middle, which is usually the case, but you can also hold the end of the board and start swinging it like a madman. Why not? I mean, that's not against the laws of physics. So technically the pivot is anywhere you want to be. Now, so torque is defined as the multiplication of those two values, which is, number one, you have to have an object that you're trying to spin. For example, like this piece of wood we're trying to spin. And then you pick a pivot point. So let's say I wanted to hold it like a bat for baseball. So I'm holding the end of it, right? So my pivot point will be the end of it. Now, so this is my pivot. Let's say I pick my pivot point over here for this question. I'm spinning it from that corner. So now, let's say someone is applying a force to push this box. So there is a force applied right here. That's your apply force. Then the distance in that equation that we want, so the force will be the apply force, right? The force right here is the apply force. What about the distance? The distance is the distance from the apply force to the pivot point, which is this. Be careful. It's not the length of the object. It's the location of the force on the object. You can have multiple people pushing the object, then you will have multiple distances and forces to worry about. So for example, if someone pushes this object from that location, then I can ensure you that the system right here is going to rotate in this clockwise direction, right? If someone is holding on to the pivot point and another person is pushing where the FA is, you don't have to push from that location. You can push anywhere that you want. The system will still rotate, right? I mean, you can push from the edge, you can push from the middle, you can push from like any location that you want. You just have to change the distance measurement. Now, the unit for distance is in meter. The unit for force is in Newton. So the unit for torque is just Newton meter, right? Not really creative, just Newton meter. Now, torque is a vector. It does have direction, but it only has two directions though. Either the torque will cause an object to go clockwise, or it causes an object to go counterclockwise. So I would like to use CW and CCW for these two directions. Okay, so either the object goes clockwise or the object goes counterclockwise. So for example, in the question that, or in the picture that we have right here, this object is going to go clockwise. Now, if you have trouble seeing which way the object will go just by looking at the force diagram, sometimes you might be able to replicate that with a physical object in your hand. Now, you all have pencils or rulers in your hand. So you can actually just pretend that wooden block right there, right? That wood block right here is a ruler or a pencil. And you try to hold it with one of your hand, and you try to push it with your other hand as the force. So if the object is in rotational equilibrium, what does that mean? That means the sum of all the torque on the objects, right? The sum of all the torque on the objects are zero. No, whoa, wait, Mr. Chow, what do you mean all the torque? There are more than one? Yes. In every single question, there are usually more than one things affecting the spinning. We just have to balance it out. That means we'll take all the torque that makes the object go clockwise, and we try to balance out with all the torque that makes the object goes counterclockwise. And when they match, your system won't spin. If they don't match, your system will spin freely. Okay, so that is the equilibrium condition for rotation. Make sure all the torque that is forcing you to turn clockwise are balanced by some torque that have you go counterclockwise. If you can do that, okay, then the system is in rotational equilibrium. Now, let's look at one example. So imagine trying to loosen the lug to remove a tire from your car. Now, you know that in that case, you will be using a wrench, right? So the idea of how a wrench actually helps you remove, so this is like what nut looks like, right? Usually you see that, if you look at any car from the side looking at the wheels, you will actually see multiple one of these. Now, you have to loosen these up in order to actually get the tires out. But have you tried using your hand to remove these? It's impossible. You will hurt yourself, you will bleed, and you won't be able to move the nut, not even like an inch. So what you need in this situation is you need a tool called a wrench. Now, the reason why a wrench works is exactly what we are learning in here, is exactly the theory behind torque. So now a wrench looks something like, okay, so you know my drawings, right? I'll try. Like this, I think. Like that. And then like this, right? It has an arm, and then you can like hold on to it. Like this. Okay, that's the best I could do. It's kind of like slanted to the side. But there we go. Okay, so you use a wrench and you fit it onto the nut and you turn the wrench. You spin it, you rotate it, either clockwise or counterclockwise, depending on how. I think usually when you want to loosen it, you're rotating it in the clockwise direction, in the counterclockwise direction. So now, let's say a torque of 24 Newton meter is needed to loosen or to tighten a nut. If a person can apply a force of 100 Newton, what is the minimum length of the wrench that is required? Okay, so here's the thing. When you're using this tool, you want to hold this tool as far to the edge, as far away from the nut as possible. Now, here's the reason why. Look at the torque equation. The torque equation has two components, right? Force and distance, right? Force and distance. Now, as you can see from this picture, if you apply a force of 100 Newton, so let's say you have an applied force of 100 Newton. So you're going to apply a 100 Newton force somewhere, right? So somewhere you're going to have a 100 Newton applied force. Now, but where do you apply that force depends on you. You can push it from here. You can push it from the middle of that handle. You can push from the very end of the handle, or you can push from very close to the nut on the handle. But where do you actually push? It's up to you. Now, but it turns out that the further you go from the center, the better it is, the easier it is for you to actually do your job. Now, and the reason why is because of this equation. As you can see in here, if you need 24 Newton meter of torque to actually tighten it. Now, your distance is 100 Newton, right? So right here. So your distance, if you look at it, that means the further away your distance is, the higher the final value of your torque, isn't it? Because these are proportional. So the stronger the force, the bigger the torque. The longer the distance from the pivot, the bigger the torque. Where's the pivot in this situation? The middle of the nut. That's the pivot, right? So the distance, when they say distance in here, is the distance measured between the pivot point to the point where you actually apply the pressure. That is the distance, right? The distance is between the pivot point and the point where your force is actually applied. So in this case, if you do your division, you will find out that the distance is about 0.24 meter. Okay, that's 24 centimeters. That means if you have a wrench, if your wrench is less than 24 centimeters long, you actually cannot even do the job. So, I mean, your wrench could be a lot longer, and then you just hold on to the 24 centimeter location and turn it, and the nut will loosen up. But of course, you can hold further. Like, I mean, it will even be easier if you're willing to hold the force a little bit further. Then you won't even need 100 Newton. You just need like 80 Newton, 70 Newton. The further you can actually move your force from the pivot point, the easier your job will be. People do this every day. For example, if you want to lift something really, really heavy, one of the ways to do it is just get a pivot point. So for example, let's say you have to lift like, let's say you're pinned down by a rock, right? Okay, so this is you calling for help, right? So you're pinned down by a rock, like a giant rock. And someone's trying to, let's say the rock is really heavy. It's like 1,000 kilograms, right? Okay. So your friend is like here. They're like, oh, I try to save you. I try to save you. Well, no one can lift 1,000 kilogram of rock. So you're still pinned down. So what can that person do is, if you can find like a metal, like a metal bar, like for example, maybe just from pipes and other stuff, like you can find a metal bar, and then so you get like a metal bar, really long, rigid, very rigid metal bar, and then what you do is you go and find another piece of rock. So you find another piece of rock and you put it like here. Okay, and then so piece of rock right here. And then you bring in the metal bar and you position it like this. Now, like this. Okay? And then, now as you can see, if this is going to turn, the pivot point is going to be here, right? So if you're turning this, like the rock is going to act as like a support. So if the person pushed down from this side, right, from the end, then this metal bar is going to rotate or spin this way. That means this side goes down, this side go up. All right. Now, but because this arm, this distance is so big, so you can have a relatively small force going down. But because this system, like this right here, distance right here, is so small, so distance 2 is so small, then the force going up will be a lot larger. So you can translate your small force into a gigantic force if you do this. Because remember, the entire system, you push down, and the distance, like these two values right here, distance and a force multiplied to a torque, which has to equal to this distance multiplied by that force from the pivot point. Those two values should be the same. So if you have a long distance, you can actually use a smaller force. But if you have a small distance, then the force on the other end will be very, very big. So this is how you use like a leverage, right, to pick up something extremely, extremely heavy. A lot of mechanics that we see in everyday life is actually based on that. So center of gravity is, for example, when we look at a beam or a piece of wood. Now the piece of wood is not weightless, right? We do have gravity. This is let's say a beam of wood. It can be a wood beam, plastic beam, doesn't really matter. Now, usually we will assume that the object has the center of gravity in the middle. We'll assume that all the forces of the object's weight is concentrated at the middle. So that's what we call center of gravity. Okay, so basically that's just where the center of mass are, where, okay, the average. Okay, so where the average mass is. Now, and that's also where we draw Fg. Okay, so we usually just say Fg. Now, of course, you don't have, like, sometimes you might have an object where the average mass is kind of not in the middle. For example, if you have like a bullet like this, isn't the average mass kind of like closer to the wider end compared to right in the middle? So that's center of mass. So sometimes your center of mass is in the middle, sometimes your center of mass is not in the middle. But to simplify our life, for physics 12, we will always assume that the beam is uniform. That means right in the middle. So we won't be doing cases where situation where we have the bullet case. So we'll always assume that this is a uniform beam. That means, for example, if this is a 10-meter stick, then we can say the force of gravity is just 5 meters in. Okay, so we'll always assume that our center of gravity is just right in the middle. So constant shape, constant density. Unless the question specifically say no, it's not, then we have to change it. All right. Now, the last point in here is just echoing a point that we made earlier, which is you don't have to actually stick with one point of rotation. You choose the point of rotation. You choose the point of, well, pivot. Okay, I guess you choose the location of pivot point. That grammar doesn't work. So you choose the location of the pivot point. Okay, so you decide which location you want it to be the pivot point. And then you start your measurement of distance from that pivot point. Now, the reason why we can do that is because if the system is not moving, right, or rotating, it doesn't matter where you point the pivot points are, it's still not rotating. So once you have a system that's stable, it should not rotate no matter how you hold it. For example, here is our first example. So we have a commercial sign. Okay, so a commercial sign right here. Now, a 350 Newton store sign hangs from a pole of a negligible mass. Now, that means they are assuming that this pole right here is massless, which I know is not reality. But for this question, for now, yes. Okay, so what is that 350 Newton commercial sign? That is this thing in here. That's the 350 Newton. It's the Jen and Eric store. That commercial sign is 350 Newton. So it's attached to here. So that means I have a force of gravity based on that commercial sign is 350 Newton. Next force. The pole is attached to a wall by a hinge. So there's a hinge right here. That's called a hinge. Okay. Okay, attached to the wall by a hinge and supported by a vertical rope on the other side. This is the vertical rope. So this system is supported by two areas. One is the hinge that is anchored to the wall. So it can spin if you cut the wire. If you somehow cut that rope, the system will spin. And then on the right-hand side, it's supported by this rope. So it's supported by two things at the same time. So therefore, on the rope, we should have tension. Right? It's a rope. So we should have tension on this side. How about on the hinge? Now, the hinge is like a nail to the wall. So technically speaking, we must have a force over there too. It's the force on the hinge. I don't know what to call it. Fy, because it's in the y direction. Force on the hinge in the y direction. Okay. Now, and then we have massless beam. Unfortunately, I know that's not something that actually, it's not something that's reality, right? You know, whatever. They say there's a massless beam. Okay, we will put a massless beam. So we don't have to add the mass of the beam itself. We don't have to add the mass of this pole itself. Okay, assuming that it's massless. Now, you look at this picture, and at this moment, you can actually tell that these two forces, Fy and Fg, and tension, they must follow our first equilibrium condition rule, meaning that the two goes up, Fy and tension, must equal to the one that goes down, Fg. If they don't, the commercial sign is going to be flying off in the air or just hitting the ground and killing someone underneath. You know that is not true. You know that tension plus Fy has to be at least gravity. Now, but that's not good enough though. That's not good enough. Only knowing that these two add together to equal to gravity, well, it doesn't tell you what gravity is, or it doesn't tell you what these two forces are. You only know that when they add together, they equal gravity. So what? I want to know how much is the tension on the rope. That is the question. The tension on the rope is the question. I can tell that. I know tension plus Fy is gravity, but so what? Like what comes after? Like how do I actually get tension or Fy? You can't. There's nothing else in this question that can help you get anything further than that, unless you consider spinning. So now we're going to consider spinning. Okay, so for spinning, you have to first decide where you want your pivot point to be. Now, there is a smart way to choose it, and there is a dumb way sometimes. Okay, the pivot point are usually put at a point where one of the forces are resigning. That means here, here, here are potential pivot point. However, the only number we have in this question is right there. So please don't put the pivot point over there because we want to at least have one number left in our picture. So we are down to either putting the pivot point on the left-hand side or on the right-hand side. Now, pivot point has a special function. Let's write that down in here. Where you choose the pivot point has a very, very special function. Okay, so let me write it down. All right, so put a big star in here. Okay, so any force, directed to the pivot point, so any force directed to the pivot point won't cause rotation. Okay, any force directed to pivot point will not cause rotation. For example, now let me give you one picture. I'm gonna put that picture here. So for example, here is a wooden pole and here is a pivot point. If you push on the pivot point, will that cause rotation? No, it won't. Now, if you don't trust me, just hold up your pencil with your finger and hold it either on the left or on the right and try pushing in from exactly the pivot point. You can make the pencil rotate by pushing on the pivot point. You can push away from the pivot point, then the object will rotate. But if you push directly onto the pivot point, no rotation. You can make your entire pencil go up and down, but you cannot cause it to rotate at all. You have to push away from the pivot point. So any force directed exactly to the pivot point won't cause any rotation, and therefore can be ignored during torque calculation. For now. Okay, so this is the art of picking the pivot point. When you pick a pivot point, you are basically killing off one of the force. That force doesn't count in our calculations anymore because that force cannot cause any rotation. So when you pick a pivot point, you need to pick one that doesn't kill off the only numbers that you have. For example, in this case, the FG in the middle, or you don't kill off the question you want to answer. You don't want to kill off the tension. So therefore, the only pivot point that we want to use is the one on the left-hand side on the Fy. Now, why would putting it there be a very good idea? Because in this case, at this moment right now, since your pivot is right there, Fy doesn't count anymore. Fy cannot cause rotation for you. The only thing that can cause rotation for you is your Fg and your tension. So Fy at that location, because that's where the pivot points are, can no longer cause rotation. Now let me draw it out. So we have our new pivot point over here where Fy used to be. And we have a beam right here. Here's a beam. And we have two forces acting on it. One is going this way, has a name of Fg. The other one is a tension that seems like it's attached to the end right here and has the word tension. Now, our pivot point is right at the beginning, right? Our pivot point is right at the beginning. So we are going to be saying that this is our pivot. Now, what about the force on the hinge? That doesn't count anymore, not for rotation. As far as rotation goes, these are the two forces that will cause rotation. Now, okay, can you tell from this picture which force causes a clockwise rotation and which force causes a counterclockwise rotation? Is Fg getting you clockwise or counterclockwise? Fg is trying to go this way. Tension is trying to go this way. You can see that, right? One force is trying to make the whole thing go clockwise. The other force is making it go counterclockwise. Therefore, they are fighting each other. Now, remember what is our equilibrium condition? just make that clockwise torque equal to the counterclockwise torque, then the whole system won't move. Okay, well, let's do it. Before we actually put numbers in, so that's 350 Newton from the question. Before we actually put numbers in, we need to measure distance. Well, what distance? Distance from the pivot. For example, the distance to the tension, can someone tell me how much that is? Looking back at the picture. How long is from the pivot to tension? 2 meters, right? How long is from pivot to the commercial sign? It's 1.3 meters. Okay, so these are your distances. D1, D2, these are different. Okay, so you're not just using one distance. All right, ladies and gentlemen, now let's write down the torque condition. In order for the torque to equal, the torque clockwise should equal the torque counterclockwise. Clockwise, we have gravity. Therefore, Fg multiplied by D2 should equal to tension multiplied by D1. Okay, so the force of gravity multiplied by the distance to the pivot is equal to tension multiplied by the distance to the pivot. And the pivot is, well, different distance away depending on like which force you're looking for. So, for example, Fg is 1.3 meters away from the pivot, whereas tension, well, tension is actually the unknown, so it's okay, leave it there. The tension is 2 meters away from the pivot. So the calculation is stupidly easy. All you have to do is multiply and divide. Okay, setting up the question in the first few rounds, you might have to think about it a bit more, but once you get the hang of it, equilibrium, I think, is the easiest topic of the entire year. Usually is. People get like insanely high average on this. I mean, that's the only equation we are learning. Like, yeah, torque. Like this equation, that's the only one. Torque equal to force times distance. All right, so 228 Newton is the tension you will find on the wire on the right hand side. Now, follow-up question then. What if people actually want the force on the hinge? Did we just murder that force on the hinge? How do we get the force on the hinge back? Well, if you want to do the force on the hinge, you have to go back to sum of forces. So we use sum of torque to help us find that tension. But once we are done, we can then go back to the sum of forces. Now, you have your hinge, you have your wire attaching to here, and you have the force on the hinge, which is called Fy, and you also have your force of gravity, which goes straight down. But at this point, you know that gravity is 350 Newton, and you know tension from the last page. Tension is 228 Newton. Wait a second, that's obvious. How can we find the force on the hinge? Whatever that's missing, right? I mean, there should be a force pointing up so that it can help tension to fight gravity. So therefore, sum of all forces, now we're going back to forces in the y direction, equal to 0. That means hinge force plus tension should go gravity. Tension is 228, gravity is 350. So hinge force must be, and then you just find out what the hinge force is. So hinge force must be subtraction between the two, which is 122 Newton. Done. That force on the hinge is 122 Newton. So in this situation, then, okay, so 122 Newton, not only all the forces balance, even all the rotation balance, this system is now in static equilibrium. That means it won't move and it won't rotate. What is the force in the x direction on this hinge? So some of you are like, Mr. Chong, is that a trick question? What is the force on the x direction of the hinge? So what is Fx? Now, you look at this picture, you look at this and you go like, but Mr. Chang, there is no other places that has a force that go in the x direction though. Yeah, there is no other places with a force in the x direction. So therefore, there shouldn't be a force in the x direction for the hinge either. You cannot have that. Okay, it doesn't exist because nowhere else gravity goes straight down. The wire goes straight up. Nowhere else could you find a force that's actually in the x direction. So the force on the hinge also has to be a 0. Now, this is going to be comparing to what we do next day. So what we do next class, continue in this last section of the topic, is going to have an object so that the wire is attached this way. So instead of attaching directly vertically to the wall, is attached at an angle. So in that situation, your tension will be at an angle, and then force of gravity, for example, right in the middle, and then you will have the hinge. But the hinge is going to have two forces now. The Fy, which together with the component, back to component of this tension, x and y component. So the Fy is going to work with tension y to fight gravity. But you notice there's one thing left, right? Who is fighting tension x to the left, to the right? Like, who is fighting this? Remember, if your answer is no one is, then this system is not in equilibrium, because that means the system will move to the right hand side. So there must be a force on the hinge that pulls it back. You must use a nail, for example, to nail that hinge to the wall so that it won't be pulled by the wire to the right hand side. So then in that case, there will be a hinge force X, which is going to balance tension X. That's Lex data. So for this setup right here, since no force is going to the right or left, then there should be no force going to the right or left on the hinge either. All right. Now, another example. So this is a seesaw tutor. You want two kids to be on it. The first kit is 65 kilogram. The second kit is 90 kilogram. Okay. So, and the board itself is 800 Newton. So that means there is a center of force of gravity, center of mass, that is 800 Newton. I'm going to name them. Let's name this FG3, which is 800 Newton. And let's put the kits in there. So kit number 1 and kit number 2. Now, I'll put kit number 1 on the very far edge and call it FG1. And I will put kit number 2 somewhere closer. Now, why? Because kit number 2 is actually heavier at 90 kilogram. If you put both of them on the edge, what happened? The game is so boring. The heavier kit will always be on the ground, and the lighter kit is always going to be up in the air, and they don't go up and down, which defeats the purpose of this game. So we want them to have like an equilibrium so that they can actually go up and down, up and down. So the heavier kit has to sit closer to the middle, right? If you have played this game in the park before, you know that. If you're playing with your big brothers, they are heavier than you, or playing with your parent, they're usually heavier than you. You ask them to sit closer to the middle, right? You sit at the very far edge, but whoever playing with you on the other side usually have to move closer to the middle in order for the game to actually balance out. Otherwise, your dad or your mom is always on the ground, and you're always just like hanging in the air and no one moves, which is not what this game is supposed to be about. So the question is, right, well, how fast do you want the 90 kilogram kit to move to? Now, I know that the 65 kilogram kit is going to sit all the way to the end. Okay, all the way to the end. But, so the question is, well, where should we ask the 90 kilogram kits to actually sit? Now, this picture is not done yet because technically I have 3 forces that goes down. Who is going up? If no one's going up, how is this system not like submerging underground? There is a very big, powerful normal force from the supporting beam. That normal force is going to be as big as all three of the force of gravity together. Let me cheat a little bit. FG1, 65 times 9.8, roughly 650, so 637 to be exact. Now, this is what I get after doing the MG, right? Let me do that one too. FG2 is going to be 90 times 9.8, which is 882. Okay, so I'm just getting these number quicker to save time, but this is basically just another MG. Okay, so we have all the forces. Technically, we can have Fn2 if I add up all three of these. That's my normal force. But I don't really need it because now we have to decide which force to kill. We need to pick a pivot point. Pick a pivot point. So your candidates are, remember, your pivot point has special power. Any force that is actually directed to the pivot point you can ignore it during the rotation calculation. So that means once you pick the pivot point, any force on that point is automatically taken out of the calculation for now, which is convenient. So use your pivot point nicely. It's like a weapon that can eliminate some enemies depending on who you want to eliminate. Our options are these. Either pivot here, or here, or here. Now let's talk about the number of forces on each point though. On here, I have one force. On here, I have two. On here, I have one. So wouldn't killing two forces at the same time be the most economical thing to do? So pivot in the middle. Okay? So you can pick which one, but then I'm teaching you strategy to make a better choice. Once you are done, usually I would like to redraw the diagram so that it doesn't have all the extra things on it. So my pivot point is in the middle. So all the forces in the middle doesn't count. I only have two other forces, FG1 on the edge and FG2 somewhere I don't know where. How do you measure distance? Now FG1 is 637, FG2 is 882 Newton. How about FG3? I don't care. It's on the pivot point. That doesn't matter anymore. Right? So, distance. I did distance, boys and girls. So, give me the distance from the pivot to the lighter kit. How much is that? How much is that? Look at your picture. How much is from the pivot, which is the center of mass, to the first kit? Is 1.3 meters. Now, how can you tell? It is correct. That entire beam is 2.6 meters, and we are putting the lighter kits all the way to the edge, which is exactly half of it. 1.3. Well, where's the heavier kit? Mr. Chung, that's exactly what we want to find. Yep, so we don't have that. That's okay. We don't know D2. D2 is the question. All right, so set up the torque equation. So all the torque clockwise should balance all the torque counterclockwise. Okay, which one makes your system go clockwise? Force 1 or force 2? Clockwise. Force 2. Yeah. If you hold your pencil in the middle, it's the force on the right hand side that makes you turn clockwise. So therefore, Fg2 multiplied by distance 2 is equal to Fg1 multiplied by distance 1. And we just substitute value, and I mean, the rest of this is very boring, right? So AA2 multiplied by the unknown is equal to 637 multiplied by 1.3. See, like the calculation is always almost insultingly easy. 0.94. So about 94 centimeters from the middle is where the heavier kit should be sitting, so that this game is not completely lopsided, right? Okay, so in this last example, we have a 3,500 kilogram truck parked on a bridge. The bridge itself is made of concrete, so it does have a mass of 6,500 kilometers. Now, what does that mean? The truck is 3,000 something kilometer, right? 3,500 kilometers. That's for the truck. The bridge, which is made of a slab of concrete, also has a mass, right? The mass is 6,500 kilograms. So two objects in here. Okay, the beam has a mass. The truck also has a mass. Okay, the truck's mass is 3,500 kilograms, and the beam, like whatever slab of concrete that this bridge is built on, also have a center of mass, which is 6,500 kilograms. So now let me draw the force of gravity. So the 6,500 kilograms. There you go. So we're gonna assume that this is perfectly centered, completely uniform. So the force of gravity from the bridge is Fg1. The force of gravity on the truck, let's assume that it is also in the middle, is called Fg2. This might be smaller though, because the truck is lighter. So Fg2. What else can you do? Well, if this is the diagram, there's no way the system does not collapse. There must be some kind of upward force to balance it. How many support do you see in here? We have two sides of support. So each of them is going to help us push up with normal force, of course. Okay, so we're going to have a normal force on the right-hand support going up, normal force. But we're going to have two. So normal force 1. And we're going to have another normal force that pushes up on the other support right here, normal force 2. Okay, so in order for the system to be completely balanced, the two red forces going down should equal to the combine of the two blue forces going up. But here's the problem. I know exactly what Fg1 and Fg2 is because the number was given to us right here. We just have to multiply by 9.8. But we have no idea how much is on Fn1 and how much is on Fn2. And they are not equal. Oh, okay. But to be fair, they would have been equal if the stupid truck was parked in the middle. If the truck was parked in the middle, then yeah, the two beams actually support them equally. But the truck is parked a little bit off to the side though. So therefore, we cannot rely on that fact anymore. In a matter of fact, because the truck is closer to the right-hand side, this will be stronger compared to Fn1 because the truck is closer to the right-hand side. Ladies and gentlemen, we can only do this with torque. And because we have Fg1, Fg2, we don't have Fn1 and Fn2, there are two giant unknowns in here. We cannot solve the equation with two unknowns. So, kill one of them. How? Using torque. Remember, if you're doing discussion with torque first, you can then set up an arbitrary pivot point. And on that pivot point, we can ignore the force for now. So let's pick the pivot point right here so that we can ignore Fn1 for now. Pivot. Okay, so once this is all done, we're going to redraw. So usually I try to redraw the picture just for like, there you go. So we have that, and we have two gravity. One is in the middle, called Fg1. The other one is for the truck, called Fg2. And then we have support on the right-hand side, which is the normal force 2. How about normal force 1? I don't care. Right? I put my pivot here. Normal force 1 is not part of the question anymore. Okay. Now, all the forces are done. I can use 9.8 multiplied by mass to get all the gravity. Now, let me just actually get all the gravity. 3,000, Fg1 is 6,500 times 9.8, which is 63700 Newton. Like, just do an mg and you will see. The truck is 3,000 kilogram times 9.8 is 3,000 is 34300 Newton. So we have these numbers. Now, but before this question can go anywhere, I need you to find me all the distance. Get me D1. Get me D2. Get me D3. every force has its own distance. I need you to look at the original picture and get me D1, D2, D3. Now, D3 should be obvious, right? The length of the beam is what? 15 meters. D3 is obvious. 15 meters. How about D1? Half of the beam, center of mass, right? 7.5. How about D2? D2 is 10. Yeah, you can see it. Because the other side is 5. So because they say, like on this picture right here, right? This side is 5. So that leaves this side as 10. Together is 15. All right. Our equations are, well, I mean, our pep work is done. Equations. Torque clockwise equals torque counterclockwise. Now, can you tell me which force is clockwise and which force is counterclockwise now? There are 3 forces. Okay, so let's start with clockwise. Which force goes clockwise? G1, FG1, FG2. They're both clockwise. So you go FG1 times D1 plus FG2 times D2. Now these two are clockwise, so then we move on. Counterclockwise is Fn2 D3. There. All the numbers that you have now can be substituted in. For example, D3 is 15, D2 is 10, D1 is 7.5. Also, all the forces that you have can now be substituted in. FG1 is 670. So, 63700. FG2 is 34300. So, the only thing you don't have is the normal force. Just grab the normal force and you're done. Right? Easy. So yeah, you have to multiply some numbers, add them together, divide by 15, but you know, that's not difficult to do. At the end, you have your normal force 2, which is the one to the right hand side. About 54700. So about 55,000, you know, roughly. That is how much pressure or force is acting on the support beam on the right hand side. Now the support beam on the left hand side is going to have a different amount of force, and I will guess that it's actually smaller because the car is parked closer to the right. So how do you get the left hand side? I mean, at this point, if you want to, you can redo this calculation but put the pivot on the other side. But the easier thing to do is just notice that, wait a second, let me write that number down here. That's something weird. Look at this. Now, I have FG1, FG2. If now I also have normal force 2, then I have everything but that normal force on the left. Can I just add the two red one together and subtract by that blue one on the left, on the right hand side to get the other one, the remaining one left? Yeah, you could. And that's the fastest way to do it. Just do sum of forces. Sum of forces in y direction should be 0. So to get the other one. So therefore, normal force 1 plus normal force 2, both go up, should equal to gravity 1 plus gravity 2, both goes down. And we have the numbers to all of these things. For normal force, we will use what we just found. 547, 00. FG1 is 63700. FG2 is 34300. Done. So just get your normal force 1, which is roughly 44300, which I want you to look at compared to our initial guess that this will be smaller. Makes sense. The one on the right hand side is about 55,000. The one on the left hand side is 43,000 Newton. So it is easier on the support on the left.